Okay, hello back. So today we are going this afternoon to see the second part of this session about adversarial examples in machine learning and how to defend against these adversarial examples using cryptographic techniques, in particular differential privacy. So now we will start with, let's say, the part on defenses for adversarial examples in general. Then we will focus in particular on differential privacy, see how it is used for data anonymization in general, because this technique actually was not invented for the sake of machine learning, but for other purposes, so for anonymizing sensitive data in certain data sets. And then we will see how we can use differential privacy for adversarial robustness. So, of course, I need to focus the window here. Yeah. So, first of all, a little question: why do we want to have adversarial robust networks? So, well, the first thing is that we will get better robust accuracy, what we told this morning about using robust features to train our neural network model in order to get an accuracy that is also robust against adversarial examples. And also, as another nice side effect, usually having adversarial robustness is also good for explainability of neural networks. So in general, there is this correlation that the more they are robust, then the better it is you are able to explain the behavior of such networks. This is because in general, the shape of the decision surface kind of becomes more interpretable by using robust features. So the idea is that with adversarial robustness, if you remember, in general, we said that we have some kind of, let's say, decision boundary to say some instances are belonging to the concept and some other instances are not belonging to the concept, or they are belonging to different classes if we are doing a multi-class classification. And the fact is that if we want to get some robustness with respect to adversarial examples, we need to take into account what we were saying today, that we allow for some slack of our input examples to be perturbed. So if they are still inside a ball of a certain radius R, then any adversarial example that is inside this ball of this radius should still be recognized as a legit example from the original class and not go into in the ball of another example, basically. The problem is that in this way, okay, here I'm using the Euclidean distance, so we have balls that look like actual balls. There on the slide you see the Manhattan distance, but it's basically, sorry, not the Manhattan distance, but the Chebyshev distance, but it's basically the same concept. So if we want to add this adversarial robustness, the problem is that we need to find, let's say, a more complicated shape for our decision surface. And the question now becomes how to do this. So there are several types of defenses, and thus to reach this kind of complicated decision boundary that is able to have this robust resistance towards adversarial examples. We could use adversarial training, for example. So inside our training set, we inject some adversarial examples already, and then we train the network as usual, and in this way, hopefully, it will become robust. The problem is that this is not very scalable in the sense that you cannot inject all possible adversarial examples inside your training set, simply for a matter of feasibility. Otherwise, there is another approach that is called network pruning. So after the training phase, so post-hoc, we are pruning some of the connections, some of the nodes in the neural networks. And in this way, we are able to, let's say, change the shape of the decision surface that has been learned by the neural network. Otherwise, we can also apply some random input transformation. So this is at test time. So this means that basically an adversary who is trying to get an adversarial example in a black box model, he doesn't have like the possibility to send it as is, because that adversarial example itself will be randomly changed before being presented to the neural network. The problem with all these three first approaches is that they are kind of empirical defenses. So they can be used to defend from adversarial examples, but usually they do not give any theoretical guarantees that they will work over any possible kind of adversarial examples under specific assumptions. So usually it is something empirical. You start by, for example, injecting some adversarial examples inside your training set, but then you see that the attacker is able to adapt to this new setting, so he can find other adversarial examples, and it means that this gives rise to a cat and mouse game, like an evolutionary arms race. On the other hand, here we focus on certified robustness, which is basically the idea of having a defense that provides a theoretical guarantee, saying that, okay, with this kind of approach, with this kind of defense, you're able to have this, to thwart adversarial examples up until you are satisfying certain hypotheses on your adversarial examples and on the capabilities of your adversary in general. So here is a small diagram comparing the two parts, like with when you are evaluating robustness in a neural network model without guarantees and with guarantees from a theoretical point of view. So without guarantees, you are having empirical defenses, basically, to protect against these kind of attacks. And the goal would be to improve the robustness against known attacks, so known adversarial examples, basically. Here instead, in the bottom part of the image, we see that we want some robust training approach or robust testing phase also, where the goal is to improve the guarantees. So even for unseen adversarial examples, we are still able to guarantee that they won't be misclassified by the neural network. So again, as in the case of the attacks with adversarial examples, what we called evasion attacks this morning, we saw that there is like a large taxonomy of works in the literature that are addressing and coming up with new evasion attacks every time. Here we have a similar situation with the thing of robustness verification. So there are a lot of works that are based on different premises, on different hypotheses. And in particular here, what we are going to focus on would be this small square here that you see on the bottom right, which are the robustness verification approaches based on differential privacy. Because basically differential privacy, in all this, it's the only technique that comes from cryptography. And this is, of course, about artificial intelligence and cryptography in general. So let's move now to differential privacy. First of all, do you have any questions so far? Everything looks clear. We are doing something very basic and mostly of a terminological nature so far. Okay, so let's go into differential privacy. But before going into that, we need to, let's say, motivate a bit what we are trying to do. So like I said, differential privacy is something that had nothing to do originally with machine learning. The idea instead was to use techniques to anonymize datasets. So suppose that we have a dataset that contains some kind of sensitive information, like for example, age, if someone has a disease or not, or this kind of information that could cause some problems to an individual if they are revealed in public. Then the idea usually is that to release this data set, you try to perturb it or to anonymize it in a way that a person outside is not able to re-identify the single records inside the database. So the two classical approaches to do this perturbation is to either suppress some attributes inside a database or otherwise to do some kind of generalization. So the problem is that these kind of approaches used in a naive way, they don't work, in the sense that as soon as you have an adversary who is a little bit more sophisticated, a bit smarter than usual, then he or she is able to re-identify individual records, even if they are like suppressed or generalized in a naive way. For example, if you have this particular database, very simple, with 6 rows, where you have names of patients inside a hospital, their age, and whether they have a particular disease or not. So you could come up with a query like, okay, I want to know what is the youngest age of a person that has that particular disease. And maybe we did some suppression on the name attribute in order to say, okay, just cancel out the name. And with that, I'm sure that there won't be any possibility to reconstruct the single record. Well, the problem is that in this way, since you see here that the age column, the age attribute is kind of an injection over the row space. So we have different values for each possible different rows. We are able to still find out what is the smallest age, the youngest age, where we have the disease. And after that, even if we don't have that particular, the name for that particular row, maybe our adversary is able to re-identify by combining this database, this anonymized database, with another database where instead there is like the name and there is like the fact that for some reason that particular patient was inside the hospital in a certain period. So in this way, by crossing these two databases, we are able to find out, to re-identify that the youngest person having the disease is Dave in this case. So naive approaches don't work in general. One of the first ideas to solve this problem came out in the late 90s by Latanya Sweeney and Pierangela Samarati, and it's this idea of k-anonymity. So the idea is that we are going to partition the row space of our database in equal-sized subsets. And in each of these subsets, we are going to do some generalization or suppression, usually generalization. The idea is that the generalization is done in such a way that rows inside the same group are indistinguishable from one another with respect to that particular attribute. So for example, if we want to group them here with respect to the age attribute, we could say, okay, I'm not going to disclose what is the exact age of each patient, but I'm going to give a range, for example, an interval of age between, for example, 30 and 39. So Alice and Bob will be grouped in the same age group. Charlie and Dave will be 40, 49 because they are age 40 and 44 years old, respectively. And Eliza and Frank will go in the last group, 50, 59. And then we say, okay, of course, we also remove the names because we are going to suppress these as well as in the beginning. And then we leave the attribute of the disease. So in this way, basically, we have a re-identification probability from our adversary, which is equal to 1 over k, where k is the size of our subsets. So in this case, an adversary would have a probability of 1/2 of saying, I'm able to find out that Dave is the youngest person having the disease, because we have both Charlie and Dave that are belonging to the same class, basically. So what is the problem? The problem is that, first one thing, these kind of principles of mechanism for anonymizations like k-anonymity are based on a kind of a straightforward principle of using many-to-one correlation. So we have a lot of secret values inside a subset, for example, the name of our patients, their age, and so on. And we want to map many of each of these secret values to a single observable value, for something that is, for example, generalized, like an interval of age. The problem with this approach are composition attacks, because these kind of mechanisms are working in a deterministic way, so there is no randomization inside it. And the composition attacks are still similar to what I was saying before in the first naive approach of suppression, but it is basically the idea of combining 2 or more queries, and then from there trying to single out a single row which can be re-identified. So if in these particular 2 databases, for example, we have from one side the same database with the age that has been generalized with k-anonymity where k is equal to 2, and the other one, the weight that has been k-anonymized also with k equal to 2. And we are going to use 2 queries and to combine them on these 2 databases, saying what is the minimal age and the minimal weight of a person with the disease. If you combine these 2 queries, then you find out that if you just apply it on a single data set, you are in the good position of applying k-anonymity, so there will be a probability of 1/2 that you are going to identify the correct row. Here instead, we are able to re-identify Dave because basically we know that he is the one that has the youngest inside that group having the disease, and also with the minimal weight. So since this is the only row, you can apply and generalize this attack also to larger data sets where you have a lot more of rows that are indistinguishable among themselves with k-anonymity, because you have a larger k, so a k larger than 2. So k-anonymity is not robust with respect to this kind of attacks. The question is now, how do we do something that is more, let's say, that is more robust in a certain sense? And the pretty idea that came out in the beginning of the years 2000, I think 2005 or something like that, is instead of saying, okay, with k-anonymity, we are going to anonymize the data set itself, so we are going to perturb it, but this we notice that has some composition problems, composition vulnerabilities, and moreover there is also another aspect that we didn't mention before. That is, if we are going to perturb the data set and to generalize or to suppress a lot of attributes, then the utility of this data is also going to decrease, basically. So we could have like a single interval for the age saying, okay, everyone from that is either 1 year old or 120 years old is inside the same group, and then the point is saying, okay, it's like you are going to suppress the whole attribute, so it's not anymore useful. Instead, with differential privacy, we are taking a different angle. Instead of anonymizing the database, we're going to anonymize the query mechanism. So the algorithm that is returning the result of a query that we want to give up. So it means that the data owner is not disclosing the data set. It is keeping it by itself on its own server. And then he gives us access to users that can pose some queries. And the results of these queries are anonymized by using a randomized mechanism. So the property that is fundamental in differential privacy is that basically if you have two databases that are adjacent among themselves, it means that they are only differing in just one row between themselves. So for example, in the first one here on the top, we have John, who is a member of this dataset, and in the other one, is not part of this dataset. Then an adversary is not able to distinguish the two situations by posing the query. So it's not able to understand whether John belongs to that database or not. And in order to do this, well, we need to, let's say, formalize what is the concept of differential privacy. So the idea is that we have a randomized algorithm A. So this means that it is an algorithm that is not deterministic, so it will give you like a different answer every time that you query it with the same input, because it has access to a source of random bits, like the probabilistic polynomial time algorithms that we saw in the first lecture for cryptography. Then we have the database, so this will be the randomized algorithm. Then we have the database D that we are trying to protect. And then we have an output space that is basically the space of the possible answers to the query. Okay, so we are going to say that A, this randomized algorithm, will be the algorithm that implements the query. So, for example, it means, okay, get me the number of all people inside a medical database that have a particular disease up to age, I don't know, 60 or something. So A is basically giving back the results for this type of query. Then we have these two, let's say, small parameters, epsilon and delta. They are called privacy parameters. Okay, and these need to be small, so something that is between the interval 0 and 1, but usually it's very smaller than 1, let's say. And okay, after we have this, we also have distance rho. This distance is able to tell us how far two databases are from each other. So in particular, we are going to use the Hamming distance. Why? Well, because the Hamming distance is the most natural one to say, okay, if we have two databases that are different only in one row, then the Hamming distance will return 1, exactly in that case. So Hamming distance will be our metric. And finally, we consider a subset of the output space where we have, let's say, some values that the adversary can try to exploit to identify a particular record. So this would be a subset of O. And this would be a subset of the output space. So the definition, you can see it here on the slide, is that we have our randomized algorithm A that is differentially private with parameters, with privacy parameters epsilon and delta, with respect to the Hamming distance, in our case, with the metric rho, on a particular database D, if for any database D prime, so we have D prime such that the Hamming distance between the two, so let's set the rho, between D and D prime is smaller than or equal to 1, so basically it is equal to 1 because otherwise we would have the same database, indeed. So they are differing only in one row. And for every possible subset of the output space that the adversary might try to exploit, then it holds that particular property. So what does it mean, that particular inequality? It means that we have the probability that the algorithm, the randomized algorithm A, is giving over the database D an answer to a query that belongs to the subset S, will be smaller than or equal to the right-hand side. And in particular, we can also write it in this way, which is maybe more convenient to see. So we can say we divide this probability by the probability that the same algorithm over the other database, so the one that is different in only one row, so the answer to this query belong to the subset S of the output space, is smaller than or equal E to the power of epsilon plus delta. So what does it mean? It means that if you do the division between these two probabilities, you will get something that is bounded by a number that is very, very small. So it means that the probability of distinguishing between these two cases is very small, or it is actually negligible, in the sense that we also defined in the first lecture on when we were talking about one-way functions. So this is the reason why differential privacy is usually considered like a cryptographic technique, because it uses a very strong condition here that is kind of reminds of the definition for the inversion of one-way functions. Actually, differential privacy then has nothing to do with cryptography itself in the sense of encryption, like we saw in the first two lectures. But still, it is considered, let's say, a technique studied mostly by cryptographers, and in fact, it was invented also by people doing cryptography. So, all clear up to now? Is this definition clear? Great. Now, we have, let's say, the question now of saying, but okay, we have this very nice definition, but how do we implement the randomized algorithm in such a way that it satisfies this particular definition of differential privacy? Well, we said that we need to find, let's say, a way to add noise, basically, to randomize the answer of our query in the algorithm. And the idea is to use basically what is called an optimal mechanism. So suppose that we have basically, let's erase here. So suppose that we have a particular prior distribution pi, which is a distribution over the possible answers to our query, basically. Then the privacy levels are still epsilon and delta. And we say that A, so our randomized algorithm, is optimal if it provides the best utility. So A is if best utility. What does it mean, best utility? We're not going to define it in a concrete or, let's say, rigorous way, but the idea is that we cannot add too much noise, otherwise we run into the problem of saying, okay, we have useless answer to our query. So we want this noise to be, let's say, small in order to preserve a utility of our query. And we will say that A is optimal if it provides the best possible utility with respect to this measure. So how do we do this? There are several ways. One of the classical ways to do it in the differential privacy literature is to use Laplace noise. So we are sampling from a Laplacian distribution. So suppose that we have our initial query, so the one that is not randomized, F, that is mapping from a set X to a set Y. And then suppose that we have the original answer, which is, I don't know, small y in the set big Y. So this is the original answer that might disclose some sensitive information to a particular observer or adversary. And so what do? We actually define this new value, Z, that will be defined in terms of a sampling from a distribution. So in particular, we say that Z will be distributed by using this particular probability density function. So the E of Y of Z will be equal to C by E to the power of minus Z minus Y divided by delta F times epsilon. So we have C, that is a constant. It's also called a normalization factor. We will see it in a minute. A is simply the number E. And it is exponentiated this particular power here, which is basically what? It is the distance between the original answer Y and the randomized answer Z. And everything is then normalized by this delta F, which is called the sensitivity factor. Sensitivity factor. And it is equal to this quantity, which is the maximum over all possible pairs x and x prime, where this particular tilde means adjacency. So they are very close to one another. They are different in one row, for example, if you are considering databases. So adjacency. So it would be the maximum of this particular distance. So f of x minus f of x prime. Okay. And finally, the normalization factor. So this C here. Normalization. Is equal to epsilon times 2 times delta f. Okay. So this normalization factor is inserted in order to get distribution, probability distribution in the end. So to make sure that what you get is something that if you compute the integral of this whole probability density function over the whole possible domain, then you get 1, as you might expect from a probability distribution. Actually, what we are interested here is something that is not distributed, like it's not a continuous distribution, it's a discrete distribution. And it is still like called a discrete, it is called a Laplacian distribution, but usually it is also called like a geometric mechanism. So it is always the same thing. So you're always computing this kind of formula here, but for a finite set, let's say for a distribution with a finite support. And okay, so yeah, in particular with this, in the discrete case, instead of having a probability density function, you have something like, okay, the probability, what is the probability of computing z given the original answer y? And this will be again the same thing as here, basically. Okay, so the idea here is that this sensitivity factor is controlling, in a certain sense, how much noise you're inputting into your, let's say, perturbed query or randomized query answer. And the normalization factor is like this. As you see, it is very simple. And this is the advantage actually of using the Laplace distribution as a differential privacy mechanism. Because it is easy to show, we are not going to show it now in a formal way, but you can look it up in the original paper by Dwork in 2006. That if you assume a Laplace distribution with those particular noise parameters, then the normalization factor is very easy to get in this way. And it has to do with the particular shape of the Laplace distribution. Actually, you can also do it with Gaussian distributions or normal distributions, but the derivation of the sensitivity and normalization factors become more, let's say, messy in a certain sense from the mathematical point of view. And okay, questions so far? Seems everything is.
We are returning Z.
Yeah, we are returning Z. This will be, so A is returning this to the user.
But delta is not used in this.
Delta? Oh yeah, the small delta. You mean? So the one, this one. Yeah. Actually, yes. You can also consider when you're doing the derivation this simpler version of differential privacy. So this is just adding an additional constraint to have an even stronger guarantee. It doesn't change that much, let's say, the structure, the derivation of the noise mechanism, let's say. But you're right. Yeah, in the, let's say, most general formulation that we also saw in the previous slide, here, we have also this additional privacy strength parameter. There is delta. Okay. Okay. So now for the part on adversarial robustness, what is the trick? Well, if you remember, we said that the image or the adversarial example is, let's say, perturbed by using, for instance, an evolutionary algorithm like the one pixel attack. And in the one pixel attack, you're going to represent the image as a vector where you say, okay, in the vector, we are going to specify what is the value of a particular pixel to be perturbed in a certain way in order to mess up the classification. So the connection between differential privacy and certified robustness, as we saw it before, is to consider the input image as a database of a sort, where each row in this database will be a pixel. So again, we will have, let's say, our image that will be identified by a long vector, and each row in this vector will be the value of, let's say, the first pixel for the first row, and second pixel for the second one, etc. So this will be our database, and at this point we can say we could apply differential privacy at this point. Why? Because differential privacy is something that is very generic. It is saying, okay, we have a randomized algorithm and we are assuming that it is used to anonymize a database. And in particular, we are using some distance like the Hamming distance that is saying, I consider all, let's say, juxtaposed databases that are differing in just one row. But the original definition is considering a generic distance row. So we can also use other kind of norm or metrics, let's say. So the algorithm now will be what? Will be the output of our neural network model. So for example, we could assume that we are trying to classify some images, for example, images of animals, and we want to get what is the exact species of an animal that we are presenting to the neural network through a picture. And A is giving in output, let's say, the probability scores for each possible animal. And then by applying the softmax activation function, we will return the argmax of this distribution. So we will have the probability that the input X belongs to the class Y1. So this is the input. Then we will have the probability that X belongs to the class Y2 until, if we have K classes like there, the probability that it belongs to the K class. So these are all probabilities. Okay. Now, what is the trick? The trick is that we want to apply a randomized algorithm that satisfies the definition of differential privacy, like we saw before in the generic case or in the case of the anonymization of databases. And if we suppose that we have a randomized algorithm A that is differential private with parameters epsilon and delta, so A is epsilon delta pp, with respect to what? Not the Hamming distance in this case, but to the p-norm metric. So the one that we saw this morning about measuring the closeness, let's say, of adversarial examples to the original input value. So to quantify the stealth and smallness properties of adversarial examples. Then if we have this particular randomized algorithm that is differential private, we can say that if we have this particular property that now we are going to unpack more in detail, then the classification model will be robust to any perturbation, to any adversarial examples, where the norm of this example is smaller than 1. So it is inside a ball of radius 1. And the idea here is that if you look at the formula, then we have, let's say that for any input image X that we might present to our neural network, and then for some particular class K, inside the possible classes for the output labels of our neural network model, then the left-hand side of that inequality is considering the expected value of the outputs that the randomized algorithm is giving, so the answers that it can give. So we have E of A, K of X, which means that we are considering all the probabilities, let's say that we are averaging them because we are considering the expected value of the algorithm A computed over the input X, so the output label given by our classification model, but randomized with this differentially private mechanism or algorithm, with respect to the class K in particular. So we are considering a single class here. So if for this class the expected value is strictly larger than that particular quantity, then the model will be robust to any perturbation. What does it mean? Well, here we have e to the power of 2. Actually, I think that should be an epsilon, not. See, here there is a small typo. Should be epsilon, I think, over I will check it later, but should be e to the power of 2 epsilon. So the privacy strength guarantee. So this is larger than or equal to the maximum, which is computed over all possible other output label. So label I, such that I is different from the label K. Of what? Of the, let me go on the new line because otherwise the camera there is not. I'm going here. So we have E to epsilon max I such that I is different from K of the expected value of the randomized algorithm computed over the input X or all possible input X for the class I plus this constant, which is very small. So it's 1 plus e to the epsilon times delta. I forgot. Okay, I forgot a parenthesis here. So here we are considering the expected value that we are taking for a particular class K, and this is larger than the maximum of the all other expected values for all other classes different from K, plus some small constant that is determined by the differentially private privacy parameters. And what does it mean in practice? It means that if you're going to see here this part of the slides, so this particular histogram, in the end, you're going to get what? You're going to get, let's say, a distribution of probabilities such that the argmax of the correct classification from the softmax is large enough that is not overlapping with any other classes. So this is what is basically implied by this formal definition here. So if we have this property that is, let's say, is basically something that needs to stand for all possible input images, and there exists at least one class K such that this property is satisfied, then we will see that if this class K, for example, would be the class of a panda, then the corresponding histogram, the corresponding bin inside the histogram, will be large enough in that we will have some stability bounds, which are these small bounds here in red, that are non-overlapping with the other stability bounds from the other classes. And this means that basically the adversary is not able to find something like, let's say, to find an adversarial example inside a ball of radius 1 in this case, because we said that alpha was had a norm that was smaller than 1 from this slide here. So any perturbation alpha here that is smaller than 1 will give rise to an histogram that is, let's say, non-overlapping the particular argmax for that probability distribution with all other possible classes or animals, like in this example. So here, what we said is the, let's say, mathematical definition of this certified robustness, but how it is done in practice. Well, for this, we are going to see in the left part of this picture in the slide. The idea is that we are going to add our noise. So the whole anonymized or randomized algorithm A will be the output, so at the end of the neural network. But actually, we're going to inject, at least this is how it is done in this paper by Lecuyer and others that was published in IEEE SMP in 2019. We're going to inject the noise only after the first layer, because they said, okay, it is enough. They noticed that you can also insert noise also in other layers, in subsequent layers, but doing that right after the first hidden layer is already enough to get this certified robustness guarantee. So there you are going to add some noise that is, if you look from the image, it's actually Gaussian noise, so it's not the Laplacian noise, that small bell curve, but it's not important. That is a technicality. The idea is that we are still able to derive an optimal mechanism for differential privacy also with Gaussian noise, and from there we are going to get the, let's say, guarantee, the theoretical guarantee that for any possible input image that is perturbed at most by something like this, something that is smaller than 1, then the corresponding argmax that we are going to get is robust in the sense that it is not going to overlap its probability with the maximum, with the upper bounds of the other probabilities. Okay? And this noise, you can see that it is always added at inference or at test time. So we are not going to do this during the training time, but it is sufficient to do it at inference, so during the test, during the evaluation on the test set. So what does it mean? It means that we have something like our, let's say, distribution in the feature space. And we have the original decision surface. Now I'm going to, let's say that these are, I'm going to cross them with x's. These are squares to say that they are different. They are different concepts, so instances of different concepts. So here we have the original decision surface that, for simplicity, I'm going to draw straight, even if generally it is not like this. It is something that it is more difficult than a linear decision surface. The idea is that the algorithm is trained in the usual way, so using backpropagation, using cross entropy as a loss function, whatever you want, and you will have the original decision surface. After that, once the adversary is going to submit one of his queries, one of his adversarial examples, then what is returned by the neural network is not the exact the exact discrimination between these two classes here, but it will go to perturb somehow a bit, but just at test time. So it is something that originally it is still straight in a certain sense, so it is the original decision surface. But when we are going to query this, we are going to perturb it a bit during the inference time. Okay, so this is the, let's say, idea of how to visualize this particular mechanism for adversarial robustness. Okay, so do you have any question or about this? Everything looks clear? Okay, so let's wrap it up for this topic for today. Then we will maybe move to something that I'm going to introduce for the lecture of tomorrow. So the idea is that, well, at least I hope I showed you that adversarial examples pose actually a realistic threat in the sense that, okay, the one pixel attack is something that has been applied to, for example, Cypher10 images, like in the Cypher10 dataset, and they are very small, so like 32 by 32 pixels. So they are not very realistic in a certain sense. But the fact is that this kind of attacks usually scale like very quickly, like with the improvement of our computational resources, computational time, then usually this kind of attacks becomes very, very efficient. So it might become like a realistic threat in a deployment of a deep neural network, for example, when you're doing computer vision for an autonomous driving car, or something like that, or for example, for face recognition or similar applications where we have pictures that have a much higher resolution. There are several types of attacks, and there are also several types of countermeasures that exist for this particular type of attacks on AI models, on deep neural networks. What we saw here is something that is very specific because it is based on differential privacy. That was originally a technique coming from the domain of cryptography to give some theoretical guarantees that let's say, a particular data set is anonymous in the sense that we are not going to perturb this database itself, but we're going to randomize the query itself, so the mechanism of the query. And if we apply it over the case of adversarial examples, then, for example, if we have some image that we are going to, that we want to perturb, an adversary wants to perturb with by changing one pixel, then we consider it as a single database where each row is one pixel, basically. And then from there, we apply the differentially private mechanism by adding some noise to the neural network once we get the description of the image. So this gives us strong theoretical guarantees that an adversary won't have any possibility to, let's say, gain some information or find some non-negligible probability of success of producing an adversarial example under these conditions. So if we have this particular differentially private mechanism that is satisfying this property, this inequality here. So there are a bit of caveats here, and that is that differential privacy, as amazing as it may sound, is not a silver bullet, of course, because there are a lot more of problems that might arise both in adversarial examples, in the sense that, okay, here you say, okay, you have a theoretical guarantees, but you're going to bound, for example, the perturbation to a particular radius. So if you're going above that radius, you don't have anymore any guarantees, and that depends on the capabilities of your adversary. And moreover, there is also this kind of misunderstanding, usually also in the literature, that differential privacy, as used in this architecture here, from this paper from Lecuyer and others, can also be used to, let's say, address problems of privacy inside machine learning. And this is actually not the case, because here it is used only for a security issue, not for a privacy issue. We will see tomorrow how we can use something else. You can also use differential privacy to address privacy concerns in deep neural networks. In actually tomorrow we will see, well, not tomorrow morning because we will have the guest lecture, but tomorrow in the afternoon we will see how to use a secure multi-party computation to deal with privacy concerns. And anyway, this is not addressed by the differential privacy setting like we used here, basically. Okay, so we are done here with this topic. Any question? Okay.